So in this video I want to quickly explain how prime numbers, HCF, which is the highest common factor, and LCM, the lowest common multiples, work. Right, so what are prime numbers? Let's start with that. Well, prime numbers is what you get at the bottom of a prime factor tree. This is a prime factor tree. It's an upside down tree. It doesn't look like a tree to you maybe, but basically this is supposed to be the root. These are branches coming out, and I did say upside down, so it's going downwards rather than upwards like a tree would. And these circle thingies are leaves. In fact, the leaves are the prime numbers. So how does a prime factor tree work? Basically you start from a root, like in our example is 60, and then you pick any two numbers that multiply to make 60, so 10 and 6 for example, and you could do all sorts of ways, but you always end up with the same leaves. That's the special thing about prime factor trees. But there are some rules about what two things multiply to make 60. Like you can see, I'm not using decimal numbers, I'm using whole numbers. And what is the other rule? Okay, yeah, so you have to pick smaller numbers than the original number. So like 60 has to be split up into smaller numbers, not the same number again. Like 60, I could have done 60 times 1, but then that, well, 1 is smaller than 60, but 60 is not smaller than 60. So basically you have to split. When you split numbers, they should make smaller numbers. You can split numbers so they make the same number twice, like 4 can be split into 2 times 2, but it has to be smaller than the original number when you're splitting numbers. So let's go through this prime factor tree. 60 is 10 times 6, and then splitting 10 you get 5 times 2 or 2 times 5, doesn't matter which way you do it, you get the same leaves. Why is 5 not splitting? Well, 5, the only way you can split 5 using whole numbers is 5 times 1. 5 times 1 is 5. There are no other numbers, and therefore we put it in a circle like a full stop. It's a leaf, and it also means it's a prime number. It cannot be split. Prime means the most basic, so if it's the most basic, that means you cannot break it down anymore. And so what is the big deal with prime numbers? Why do they make up this funny thing? In math there's always a reason for making stuff up. It's not completely useless, right? So these prime numbers, they are the building blocks of all numbers. So if you multiply all these prime numbers together, you get this thing here. You get the original number. So basically all numbers come from prime numbers. If you multiply prime, they can be like a so you can multiply, how can I say it? So all numbers are products. Products means when you multiply two things together, like when the sum of two things, or when you add two things together. So all numbers are products of prime numbers. They are made of prime numbers. So 60 is made of 5 times 2 times 3 times 2. Now one thing I haven't written here, these are incomplete notes, but I really wanted to replace my older ones because it uses some method which isn't really as cool as this method I'm going to show you. So there's two sentences I want to say that I haven't actually written down here. So 60, writing 60 as a product of its prime factors. So I say product, right? I've said, where have I used the word product? Product there, right? Product means when you multiply two or more things together, right? So writing 60 as a product of its prime factors, factors, yeah. The factors are, well, we're going to talk about factors in a minute, but factors are things that go into other things. So a factor of 60 is 10 or 6, or actually all of these things, these are factors of 60. They go into 60. So 6 goes into 60 because 6 times 10 makes 60. 12 goes into 60 because 12 times 3 makes 60, blah blah blah. So you get what factors are, right? So if I want to write 60 as a product of its prime factors, it's equal to 4 times 2 times 3 times 2. just multiplying all these leaves together, right? These prime factor leaves together. And the other sentence after product of prime factors is product of powers of prime factors. So instead of saying 5 times 2 times 3 times 2, this 2 times 2 can be squeezed into 2 squared. So I could say 5 times 3 times 2 squared is the product of the powers of prime factors of 60. Right, hopefully that made some sense. Right, and forget this, it doesn't matter. I've already explained this. Now we're going to use our prime factor trees and our prime numbers to do something even more clever. We are going to find the HCF, the highest common factors, and the lowest common multiples, the LCM, of 40 and 60. But before I do, I want to explain this phrase and this phrase, right? And both of these, well, both of them have something about common, right? The word common means when you have something the same. And to have something the same, you have to have at least 2 things that are sharing it. So you have to have like 40 and 60, or maybe in this next example I have 24, 48 and 54. What do they have in common? What do they have the same, right? So to have something the same, you have to have at least 2 things that we're talking about. Blah blah blah. Let's talk about the highest common factor especially first of all. So let's list the factors of 40 and 60. So these are the factors of these are the factors of 40, and these 1 2 3 4 5 6 10 12 15 20 and 30, these are all factors of 60. And like I just said a minute ago, factors are things that go into another number. So a factor of 60 is, for example, 3, because 3 goes into 60. When I say goes into, that means 3 times something makes 60, or 60 is in the 3 times table, for example, or 60 is in the 10 times table. That's another way of looking at it. Right, so what else is there to explain about this phrase, highest common factor? Because that's what we're doing in this example. We're just talking about highest common factor. In this example here, which we're coming to, we will explain lowest common multiples. So we've talked about the factors, the F in the highest common factors of 40 and 60, and now let's talk about common factors, the C bit of this phrase. So the C bit talks about the factors as well, the common factors though. So the common factors are the ones I've highlighted by connecting a line, so you can see what's common. So you can see 1 is common to this list and that list, the factor list of this of 40 and the factors list of 60. 2 is common to both lists. 5 is common to both lists, etc., etc., right? And then we want the highest common factor. So the highest one of these common factors. So the highest one of these numbers that are linked between the 2 lists. So obviously this is the highest one, 20. 20 is the highest common factor, the HCF of 40 and 60. Next we're going to talk about lowest common multiples. We've already talked about what common means, what's the same, but let's talk about what multiples are. Well, multiples are things that are, well, what's a multiple of 40? Notice I haven't put the kind of underline like I did there, because these are incomplete notes, but it doesn't matter. I just wanted to get these this video out to replace the other video I've got for this, which is not so good. And for people who don't know my videos, I use these for my students, and I want this way of doing it rather than the old way of doing it. That's why I'm making this video very quickly. It's much better, this method. So anyway, what are the multiples of 40? Well, 40, 80, 120, because basically the things that are in the 40 times table are the multiples of 40. Multiples comes from the word multiply. So what can you multiply 40 by to get other numbers? 40 times 1, 40 times 2, blah blah blah. So these are the multiples of 40, these are the multiples of 60, and these are the common multiples. I've I've shown links between what's common in both of these lists, and this time we don't want the highest common multiples. You can't really get the highest because this list goes higher and higher and higher and can go on forever, so you can never get the highest common highest common multiple, but you can get the lowest common multiple, which is this 120. 120 is a multiple of 40 and a multiple of 60, and it's the lowest one of them. Like there's another one, 240, but that's higher. It's not the 240 is not the lowest. 120 is because it's lower than 240. Blah blah blah. You can see what I'm talking about. All right. Anyway. So that is what these phrases mean, HCF and LCM mean, but that's not the proper way of doing it because that's a bit slow. These are the slow ways of doing it, especially when you get to even bigger numbers. This way just goes wrong. It will go wrong. One way this will go wrong is that you'll probably miss out something from your list, and then you're in trouble, because if you miss out like the key number that we're looking for, then the whole thing will go wrong. Anyway, let's do it the proper way. The proper way is you make factor trees like we showed a minute ago over here. Right, so you do factor trees of the things we're trying to find the HCF and LCM for. So in this question we're going to find the HCF and LCM for 40 and 60, which are actually the same numbers we were doing examples for here, right? So we should get the same answers in a minute. So finding the factor tree for 40, let's do it together. What are two numbers that multiply to make 40? Well, 10 and 4 could be one possible answer. Remember, you can do it any way you like. You always get the same leaves at the end. So I chose 10 and 4. 10 times 4 makes 40. Then I have to split the 10. Well, 5 times 2 makes 10. And I can't split 5 because only 5 times 1 makes 5. And remember, I said the way you make these prime factor trees is that you have to get two smaller numbers than the original number. So if I do 5 times 1, well, 5 times 1 to make 5. Well, 5 is the same as 5. It's not smaller. So basically, that is a full stop. It's a leaf. It's a full stop in the sense that you cannot carry on. Same with 10. Same with 2. You cannot split 2 into two smaller numbers that multiply to make 2. So 2 is also a leaf or a prime number. And you can do the same with 4. 4 is 2 times 2. 6, let's do 60 now. 60 is 6 times 10. Splitting 6, you get 3 times 2. Splitting 10, you get 5 times 2. Blah blah blah. There isn't much to say about that. Let's talk about this thing. How do you actually get the HCF and the LCM from our prime factor trees? Well, this little circle is supposed to belong to all the factors of 40, and this circle here belongs to all the factors of 60. And where the two circles, they're not really circles, they're ellipses or whatever, where they overlap, which is this bit here, is what's the common bits, what's same to what are the common leaves or prime numbers in 40 and 60. So when you make these circles, you start off empty and you list first of all the common bits. So what's common in both of these trees? What are the common leaves or prime numbers in the 40 tree and the 60 tree? Well, you can see there's a 2 here and a 2 in this tree. So what I would do, these are incomplete notes, I would cross them out as I go along. So I cross this out, so that I know that I've said these ones overlap, or I mean these are common, right? And so I don't use them again. Then I go for another number. What else is common? Well, this 2 can match with this 2. This 2 could match with this 2 as well. They're the same number, right? But I just cross this one out and cross this one out. You can't see from the notes because I haven't shown it, but I've already crossed this one out if you remember. So I crossed these 2 out and I crossed these two 2's out. And then I go, what else is common? Well, this 5 matches with this 5. So cross this 5 and this 5 out, and there's nothing else that's common. Like this 3 cannot match with anything here because there's no 3 there. That's it, really. So there's basically 2, 2 and 5 that's common between 40 and 60 in their trees. So 2, 2 and 5 are the common bits, and in fact if you multiply those together you get the HCF. If you multiply the common bits, the bit that goes into both of these circles, you get the HCF. 2 times 2 times 5, 2 times 2 is 4, 4 times 5 is 20. 20 is the HCF, and it's the same result as we got here. It should be the same result if you did it the right way, of course. And the LCM is just the HCF number, which is 20, times the other numbers that are left over. So these are the leftover numbers that we haven't used so far. Well, we talked about the stuff that was common, and the stuff that was not common goes there. So 2 is in the 40 circle, but which was not used in the common bit. So there was 2, 2 and 5 which he used, and this 2 over here was left over, so that goes in this 40 circle. So if you look at this circle, there's 3 2s and a 5, 3 2s and a 5. Okay, so that's all the prime numbers that go into 40, and in this circle are all the prime numbers that go into 60. So 2 2s, a 5 and a 3. 2 2s, a 5 and a 3 goes into 60. And we've already used up these common numbers, the 2, 2 and a 5, so what's left is the 3 that goes in this circle over there. And so the LCM, the lowest common multiple, is the HCF, which is this stuff, which makes 20, multiplied by the rest, and the rest are the 2 and the 3 over here. So 2 times 3 is basically 6. 6 times 20 is 120. 120 is the lowest common multiple, which is what we got earlier on over there for 40 and 60. Remember, we're doing 40 and 60, the same numbers. Right. What's next? We're going to find the highest common factor and lowest common multiples for 3 numbers this time. Last time we just did it for 2 numbers over there, right? So let's focus on this. What are the HCF and lowest LCM for 24, 48 and 54? Well, as before, I'm just trying to whiz through this video now. You can pause it if you like and see how I did the prime factor trees for each of them. But this time what's different to the previous example is that we've got 3 numbers, which means we need 3 circles. And the bit that overlaps all of them, so all 3 overlap in this middle bit here. You can see this circle belongs to 24, this circle belongs to 54, and this circle here belongs to the 48 over there, right? And you can see that here, like look at this. This circle is 2 times 2 times 2 times 3. 3 2s and a 3, 3 2s and a 3. This circle are 3 3s and a 2. 3, 1, 2, 3 and a 2. This circle belongs to 54, and the 48 has got the most prime factors, got 4 2s and a 3. Like here can you see 1, 2, 3, 4 2s and a 3. So this circle is the circle for 48, the circle which contains all the prime numbers or prime factors of 48. Right, and so where they all overlap, all 3 circles overlap, is over here. So that means 2 and 3 are the bits that are the same in all 3 trees. So the way you do it, the way you go about doing it is you always start with the bit that's common to all of them, and then you start finding the bits that are common to maybe just 2 trees, and then you do the leftovers. Right, so let's do that together. Not brilliantly because I'm not actually drawing on this, but in another video I'll do it better. You can see 2 is there, so I'll cross that 2 off, and there's a 2 there, so I'll cross that 2 off, and there's a 2 there, so I'll cross that 2 off. So you have to imagine this 2, and this 2 are all crossed off. And then I say what else is common? Well, there's a 3 here, and a 3 there, and a 3 there, so I cross those off. And so those are the only bits that are common. Then I go, what else is common between any of them? Well, I've crossed off this 2 and this 3, but there's these left over, right? These 2, and these 2 actually match up with these 2. There's no more 2s to match up over there. I've used this 2 up, by the way, right? So that would go in this circle and this circle, because this circle is 24 and this circle is for 48, and they both have 2 2s that are not used in the other common bits. Right? So 48 also have 2 and 3 common, but I've already used that in this bit of it, right? And these are the 2 2s that are left over. So that's like all these numbers used up, and 48. Well, I've used up 2 2s, and I've used up a 3 and a 2. Basically, I've used up 2 3 2 2, but I've still got 1 2 left over, and that can go over there. That's in the kind of leftover zone of the 48 circle. Right? It's not really a circle; it's an ellipse, but whatever, right? So, and then in the 54. Remember, we used up the 2 and a 3, but it also had these factors here, 3 and 3, so that goes there. So that's how you make these circle things, which the proper name for it is Venn diagram, but I don't want to use big words, right? You don't have to remember that it's called a Venn diagram. You'll learn about Venn diagrams maybe later on. So that's how you draw these circles, and like I said before, the HCF is the bit that's common to all of it, which is this middle bit here, not this bit here, which is only common to 2 bits. This middle bit here is in all 3 circles, so 2 and 3 are the common factors to all 3 trees, all 3 numbers, 24, 48 and 54, and if you multiply them together, 2 times 3, you get 6, which is the HCF. And the LCM, like I said before, is the HCF bit times the rest, which is all this other stuff. So if you multiply all this other stuff, 2 times 2 times 2 times 3 times 3, you get 72. And like I said before, the middle bit was 6, so 6 times 72 is 432. We've basically got the LCM. Not basically, we have got the LCM. The LCM for 24, 48 and 54 is 432, and the HCF for 24, 48 and 54 is 6.